The vast center of Yellowstone National Park looks like land the Rocky Mountains forgot. Ranges hem the heart of Yellowstone on all sides: Madison, Gallatin, Absaroka, Beartooth, Teton. So what's going on? After all, the flatland in much of central Yellowstone has experienced many of the forces that elsewhere produce towering mountains. Yellowstone itself technically forms a part of the Rocky Mountain chain. Nevertheless, relief, that is, the difference in elevation between highest and lowest places on the Yellowstone Plateau, is relatively subdued. North-south mountain ranges that flank the park have conspicuous gaps where you might expect them to cross Yellowstone. Assuming, reasonably, that these ranges once traversed the park, where the heck did the mountains go? The answer's simple. During the enormous eruption that took place at Yellowstone some 640,000 years ago, either the collapsing volcanic caldera swallowed them, or the eruption itself blew them away. The mountains are gone, in essence, because Yellowstone ate them. This kind of transformation is evident all around when you visit Yellowstone. Whichever direction you choose to enter, and wherever you go, you are confronted with natural marvels, many of whose origins are geologically recent. I'm not just talking about the geothermal features produced by hot water in the park. I'm talking about mountains and valleys shaped by fiery caldera eruptions and frozen rivers of moving ice. Now, it's true that some still visible features of Yellowstone date from much earlier than the immense volcanic eruptions that radically transformed the landscape. Shallow inland seas repeatedly flooded the Yellowstone region over the past 500 million years, leaving material for sedimentary rocks. Shale and sandstone as deep as 10,000 feet are present. Early mountains built 75 million years ago and more, long since deeply eroded, are still visible in places in and near the park. But most of Yellowstone has been transformed by the relatively recent eruptions. Even beyond its travertine terraces and geyser basins, every corner of the compass points to geological novelties at Yellowstone. Arriving from Gardner, Montana via the park's north entrance, as many do, you pass through a historic stone arch made of volcanic basalt. President Theodore Roosevelt laid the arch's cornerstone in 1903, and across the top it reads, "For the benefit and enjoyment of the people," language from the congressional act that created this first national park in 1872. South of here, past the steaming, cascading terraces of Mammoth Hot Springs, lies Obsidian Cliff, a rare wall of volcanic glass formed 180,000 years ago. Obsidian forms when a silica-rich lava cools too quickly for mineral crystals to grow within it. The Obsidian Cliff may have formed even more quickly, perhaps when lava came into contact with a glacier. Native Americans prized obsidian for making spear points and other blades, since, lacking the internal atomic structure of minerals that fracture along specific planes, obsidian breaks in concave arcs that yield razor-sharp edges. Geologists call this property conchoidal fracture, and it's actually reminiscent of the cupped whorls of a conch shell. If you'd like to see an up-close example, just drop a china plate on a hard floor. Or not. In George R.R. Martin's Game of Thrones books and the HBO series, the denizens of Westeros refer to obsidian as dragon glass, an apt enough name given that it's indeed forged in fire. Obsidian is mostly silica, but each sample always includes a unique ratio of rare elements. It's in fact possible to use this chemical signature to determine the provenance of ancient spear points, that is, where they came from, and so to determine whether they came from Obsidian Cliff here at Yellowstone. A freshly exposed obsidian surface also develops a so-called hydration layer as it absorbs water from the surrounding air. The thickness of hydration layers on obsidian blades reveals their approximate age. Using these techniques, archaeologists and geochemists have determined that Native Americans were crafting spear points from obsidian cliff glass more than 10,000 years ago, not long after the retreat of the most recent glaciers that covered the region. More recently, blades from this very cliff were imported and prized by distant Indians in what is today Ohio, before the arrival of Europeans in North America. The road into the park from West Yellowstone follows the Madison River. Anglers casting for trout might be there depending on the season. Above looms a long, steep ridge. That ridge is part of the wall of the caldera, the giant basin created by the last supervolcano eruption. Yellowstone Lake in the southern portion of the park is the largest high-elevation lake in North America, 132 square miles at a surface elevation of 7,700 plus feet. At the West Thumb Geyser Basin on the lake, Fishing Cone Geyser earned its name from early fur trappers and traders, the so-called mountain men, who alleged that it was possible to catch a fish in the lake from shore, drop it in the cone, and cook it without ever removing it from the hook. I can't vouch for the plausibility of doing this, never having tried it myself. To the northeast, in Lamar Valley, you might encounter descendants of some of the wolves reintroduced into Yellowstone in the 1990s. The species was virtually eradicated here by 1926, during an era before folks recognized that wildlife, as well as landforms, merited protection in the national parks. Not far from the valley, stone walls exposed in ridges resemble massive pencils standing upright, or, say, the side of a huge dark honeycomb. If that's what these were, I'd hate to see the bees that made them. Well, the walls aren't pencils, and they aren't honeycombs. They're columnar basalts. They are columns of basalt that form when a lava flow shrinks as it cools, whether at its surface or at the interface between underlying cooler rock and the cooling lava, then fractures in prismatic, roughly hexagonal pattern. You might find 5, 6, or 7 sides on the columns. A familiar example of a similar process is the way mud cracks form when mud dries and shrinks, forming a pattern of polygons when viewed from above. As the pattern of fractures makes its way downward through the thickness of a chilling lava flow, it forms these long, pencil-like shapes. Devil's Tower National Monument in eastern Wyoming is another famous example of columnar basalt. The Continental Divide, high ground separating the Atlantic and Pacific watersheds, passes through the park from northwest to southeast. Streams to the north and east of the divide flow into the Madison and Yellowstone rivers and on to the Missouri and the Mississippi before reaching the Gulf of Mexico and the Atlantic Ocean. Streams to the south and west find their way to the Snake River, on to the Columbia, and ultimately to the Pacific. Lewis and Clark, seeking a relatively easy path across the continent, might have saved themselves the trouble of crossing the snowy Bitterroot Mountains if they'd come this way instead. So much of what we encounter here in Yellowstone resulted from a trio of caldera eruptions, staggering in scale, and a multitude of minor ones. They left their indelible signature on the landscape in and around Yellowstone. A caldera eruption is one in which a large magma chamber empties itself in one big volcanic event, and its ceiling, which happens to double as the ground above it, gets blasted away or caves in. The first and largest, my kids would say most epic, of the caldera eruptions at or near Yellowstone occurred about 2.1 million years ago. This first eruption produced the vast Huckleberry Ridge caldera that encircled much of the park and regions west of it, along with an associated layer of welded ash and other debris called the Huckleberry Ridge Tuff. Another smaller but still ginormous, that's a technical term, eruption some 1.3 million years ago formed the Island Park caldera and created the Mesa Falls Tuff. The third major eruption produced what we call the Yellowstone caldera, larger than the second, smaller than the first. Also known as the Lava Creek caldera, the ash bed it scattered across much of the continent was the widest ranging of the three, at least from the traces we have, reaching as far as Southern California, Louisiana, and beyond North Dakota. This caldera encompasses much of central Yellowstone National Park. Subsequent lava flows that filled in much of the caldera and glaciation have obscured the sharp outline of the third big caldera, but that high ridge along the Madison River is a surviving portion of its rim. All told, the Yellowstone caldera measures about 45 miles long from northeast to southwest and 30 miles wide. This is far longer and wider than calderas of other familiar volcanoes. The diameter from Mount St. Helens, about 1.5 miles. Kilauea on the Big Island of Hawaii, about 2.5 miles. And Crater Lake, formed by the prehistoric eruption of Mount Mazama, about 6 miles. Another meaningful way to get a handle on the scale of the big Yellowstone eruptions is to look at the volume of stuff that they erupted, both liquid lava and fragmental material called tephra, such as ash, pumice, dust, and chunks of rock called volcanic bombs. The first big caldera eruption, Huckleberry Ridge, blasted out something on the order of 600 cubic miles worth. By comparison, the 1980 Mount St. Helens eruption was estimated to have unleashed only 1/4 of a single cubic mile's worth. The Island Park caldera disgorged about 67 cubic miles of material, just over 1/10 as much as Huckleberry Ridge, but still an enormous volume. And the most recent, the Lava Creek or Yellowstone eruption 640,000 years ago, coughed up 240 cubic miles worth of volcanic material. That is a monstrous volume by any measure except, perhaps, that of the Big Daddy Huckleberry Ridge eruption. All three of these caldera eruptions were much, much, much larger than any sort that's taken place during historical times. Wind carried ash from each around the globe, and it piled in drifts across most of what is now the western United States. Dust and other aerosols pumped into the stratosphere during the eruptions would have cooled the planet dramatically for years. What sequence of events led to these colossal eruptions, you ask? And, gulp, could it happen again? Good questions. Today, swelling and deflation of the gigantic magma chamber beneath Yellowstone as magma shifts about or is added from below causes the land above to rise and fall by up to about 1 inch a year over a number of years. It's almost as if the park, like a slumbering giant, were breathing in slow motion. Or perhaps like two slumbering giants. Land in the park bulges upward at 2 large domes that were eruptive centers during the last caldera eruption, one called Mallard Lake near Old Faithful, one called Sour Creek north of Fishing Bridge near Yellowstone Lake. These two rise and fall, not concurrently, but on their own timetables. It seems likely that the magma chamber beneath Yellowstone has been similarly dynamic for much of its history. Now, much as I can't eat too much Thanksgiving turkey without risking the loss of a shirt button, swelling as the magma chamber below Yellowstone fills stretches the brittle land above it. This swelling produces fractures, breaks in the rock, and faults, surfaces across which relative motion occurs. These fractures and faults form in concentric bands, similar to the rings on a dartboard. Shaking from earthquakes associated with motion in the magma chamber and on the faults helps to create even more fractures in the stressed rocks. Occasionally in the past, pockets of magma reached up to the surface, or a fault from the surface reached down to the magma, resulting in an eruption on more modest, familiar scales. But when, say, a rupture occurred on one or several of the concentric faults, reducing pressure across a large lobe of the magma chamber and causing gas bubbles to form within it, this would have triggered a catastrophic eruption. Why so? Why do mere bubbles cause a catastrophic eruption? It's because the magma beneath Yellowstone is so highly viscous, thick and sticky like tree sap, making it impossible for a large volume of gas to bubble away and escape. A relatively high concentration of silica, that is, silicon and oxygen, in the magma accounts for this, since silica forms long, sticky chains in the melt. You may be familiar with such chain-forming behavior from the element carbon, the basis for organic molecules and life. Silicon sits directly below carbon on the periodic table of the elements, and so displays some similar properties. Think of silica in a melt as liquid Velcro. When a lot of bubbles form in a silica-rich magma due to a sudden reduction of pressure, and the magma doesn't contain lots of water that might help make it more fluid, the magma simply explodes. As it blows up and apart, the magma transforms into hot gases, dust, ash, and chunks of pumice. Pumice forms when lots of gas gets trapped inside to form a type of soft rock that resembles meringue and is so chock full of low-density ash and air pockets that it floats on water. It's this whole mix we call tephra, the pumice, hot gas, dust, and ash, which together, 1, blows the lid off the magma chamber, and 2, vents at the surface with a vengeance. The trio of huge magma chambers at Yellowstone emptied themselves in and around what would become the park, deflating like balloons. Perhaps the Hindenburg is a more apt analogy. What land remained above collapsed into the calderas, falling as much as 2,000 feet by the time the eruption had ended. Whole mountains vanished into these chasms or were ripped apart and scattered around them. Then ash and other hot ejected material inundated the surrounding land, leveling the landscape by filling some valleys. Other ejected material fused into so-called welded tuffs, hundreds of feet thick, all around the calderas. These are the Huckleberry Ridge, Mesa Falls, and Lava Creek tuffs we find today, mute witnesses to catastrophe. Even if we know the sequence, you might ask, how do we know roughly how long ago each of these cataclysmic eruptions took place? The predictable transformation of potassium-40, a radioactive isotope, to argon-40, one of many types of radiometric dating used by Earth scientists, offers one powerful line of evidence. Being an unreactive, noble element, argon doesn't form compounds with other elements, and so would have been absent when minerals containing potassium formed from cooling lava. Over time, however, argon-40 produced by the decay of potassium's radioactive isotope accumulates within them, where it's trapped inside and can't escape. The many potassium-bearing minerals found in volcanic rocks at Yellowstone thus each contain a tiny stopwatch. By measuring the ratio of the parent, potassium-40, and daughter, argon-40 isotopes within them, we can calculate their ages. And this is what geologists have done. After each of the major caldera eruptions in and near Yellowstone, a succession of additional smaller eruptions released yet more material, backfilling much of the deep calderas and obscuring their outlines. The most recent of these occurred at Yellowstone about 70,000 years ago, when a large lava flow buried cliffs and gullies to form the park's Pitchstone Plateau. Another eruption, more violent, blasted the west thumb of Yellowstone Lake into existence about 174,000 years ago. The Upper Geyser Basin, including Old Faithful, is nestled between several lava flows that passed it by. All this subsequent volcanism, less titanic in scale, is why it may be difficult for a park visitor to grasp the sheer immensity of the caldera surrounding the Yellowstone Plateau, and of the profound havoc it wreaked for dozens of miles in every direction. So why did this trio of severe eruptions occur in and near Yellowstone, and why does this huge magma chamber lurk, not so quietly, beneath the park today? The answer lies with something called a hotspot in Earth's mantle that's blazed a trail, both figuratively and literally, across the northwestern United States over most of the last 20 million years. It is this hotspot that feeds the magma chamber beneath the park and is the furnace of the Yellowstone supervolcano. To appreciate how this hotspot has transformed the land above it, we need to understand a bit about Earth's interior and some of the extraordinary facts of plate tectonics. Consider an idealized cross-section of our planet. It's concentrically nested like Russian dolls, Matryoshka dolls, one inside another inside another. Earth has three main layers from the standpoint of the strata where different elements predominate. A dense core, comprised mostly of iron and nickel. A less dense mantle, and understand this is not to scale, surrounding the core and comprised primarily of silica and magnesium and iron oxides, and an even less relatively thin crust with an even higher abundance of silica, less magnesium and iron than the mantle, and more aluminum, potassium, and other lightweight elements. The physical properties of each element can vary depending on pressure, and that allows us to distinguish additional boundaries. The inner core is solid, while the outer core is liquid. Similarly, the elements of the lower mantle are solid, while there's a zone in the upper part of the mantle where the combination of pressures and temperatures allow rock to flow, albeit slowly. This zone starts at depths of anywhere from about 60 to 120 miles, and ends at depths as great as about 400 miles. Geologists call this zone the asthenosphere, from the ancient Greek asthenes, meaning weak or frail. Above the asthenosphere, the outermost mantle and the crust on top are solid. These uppermost solid layers are relatively thin and brittle, akin to the shell of an egg in scale. They're called the lithosphere, derived from the ancient Greek lithos, meaning rock or stone. Some use the analogy of a sandwich cookie with cream filling to describe the relationship between the three layers. The solid lower mantle, bottom cookie, the ductile asthenosphere, cream stuffing, and the solid lithosphere, upper cookie, though the rocks of the Earth are decidedly less delicious and tougher on the teeth. The two cookie layers can slide alongside one another across the cream filling, and sometimes one of the cookies breaks. What about the underground fluids? Water in a pot on your stove heats above the burner. The water expands as it gets hot, so it becomes less dense and rises. At the surface it cools, becomes denser and sinks. This circular flow is called convection, and convection helps drive the flow of water through Yellowstone's geothermal basins. Convection, along with gravity, also helps drive the motion of giant rigid plates that cover Earth's surface. We call this motion plate tectonics. Geologists have identified 15 plates, 7 primary, 8 secondary, and several dozen tertiary plates, spanning the planet's surface today. Yellowstone sits unquietly within the North American plate. A cross-section of the Earth deep beneath Yellowstone reveals a hotspot below. This is a massive heat source, or conduit in the mantle, that provides both warmth and partially molten rock to inflate the magma chamber in the crust just below the park. The heat and magma rise toward the surface in what's called a mantle plume. Seismic waves generated by earthquakes pass more slowly through partially fluid rock than through solid rock, and scientists have used this fact to create three-dimensional images, such as this one of the plume rising from the Yellowstone hotspot, as well as the magma chamber. For millions of years, the Atlantic Ocean has grown along a rift in its basin called the Mid-Atlantic Ridge, becoming wider as the Pacific Ocean shrinks, contracts. To accommodate the Atlantic's growth, the North American plate has crept southwestward at a rate of about 1.8 inches a year relative to the mantle below, including the Yellowstone hotspot. To visualize the result, think about what happens if you pass a sheet of paper over a lit candle. The candle's flame traces a singed line along the sheet, possibly burning through in several places. This is what the Yellowstone hotspot has done to the North American plate. It began about 18 million years ago near what is today the border between Nevada and Oregon. Someone on the Nevada side of the border must have rolled snake eyes, metaphorically speaking, and multiple caldera eruptions burst through the land, scorching it, scarring it, and creating the McDermott volcanic field. The process repeated itself again and again across northern Nevada, then into and across southern Idaho, tracing a path of devastation and creating a sequence of Yellowstone-like calderas across the Northwest, before reaching northwestern Wyoming a few million years ago. One final signature of the Yellowstone hotspot's passage was the release of vast quantities of basaltic lava. As North America continued its long, slow slide to the southwest, and these blasted landscapes moved away from the hotspot, they typically would have descended more than 1,000 feet in elevation, since the hotspot lifts up the land above it. As this occurred, fracturing and faulting provided conduits up which a new sort of magma made its way to the surface. This lava had a lower concentration of silica and was therefore more fluid and less viscous, so less explosive than most of the lavas released during the caldera eruptions. The fluid lava flooded and paved much of the hotspot's trail, burying it beneath basalts. In its wake, the Yellowstone hotspot left the central and eastern portions of the Snake River Plain, a trail that leads straight to Yellowstone. Winds at the latitude of the park blow primarily from the west. And so, today, this plain, cleared of big mountains, acts as a conduit for moisture-laden air blowing in from the Pacific Ocean. This helps to give both the Yellowstone Plateau and Grand Teton National Park, just to the south of it, more rain and snow than they would receive otherwise. Fertile soils on the basalts have also helped make Idaho famous for its potatoes. Central Idaho's Craters of the Moon National Monument and Preserve, which is also managed by the National Park Service, bears witness to the aftermath of the Yellowstone hotspot's passage. It includes basalt lava flows and more than 25 volcanic cones, and has experienced repeated eruptions over the last 15,000 years. Though dormant now, geologists predict that eruptions will likely occur again at Craters of the Moon within the next 1,000 years. Hotspot-driven volcanic fire tells much of Yellowstone's story, but we mustn't neglect the ice. Some 22,000 years ago, at the height of the most recent glacial advance, called the Pinedale Glaciation here in the Rocky Mountains, the Yellowstone Plateau lay buried beneath about 4,000 feet of ice. This ice sheet completely covered not just the park's lowlands, but also the summits of Mount Washburn and Mount Sheridan. Only the highest, jagged peaks of the Absarokas pierced the surface of the ice to peak, with two E's, out above it. What would become Yellowstone Lake lay buried beneath nearly a mile of ice. This ice scoured out the land below and depressed it as well, as some of the soft asthenosphere flowed out from under the ice-burdened, down-bowing lithosphere. Now we can only imagine walking for miles and miles across the blindingly white Yellowstone ice sheet on a clear day 20,000+ years ago. You can visit identical environments to the north, in the Canadian Rockies and Alaska. Within settings such as the Columbia and Harding ice fields, over expanses of hundreds of square miles, only the crests of a few high volcanic summits and a ring of mountains at the edges of the sheet pierce an otherwise endless-seeming field of ice overlain by snow. To stand at the center of such an ice cap is to feel adrift on a cold, white ocean. Glaciers are Earth's great leveler. They may appear static, just incredibly thick piles of snow, but they're always on the move, just as a glacially slow rate. As snow and ice pile thicker and thicker, the weight transforms snowflakes into a compact form called firn, then firn into denser forms of ice. And not just denser ice. The tremendous pressure of all the ice above causes some of the bottom of a glacier to melt and flow. This is why glaciers flow outward and downward toward places where the ice can melt or calve off into water and get carried away. Glaciers are massive conveyor belts for whatever they can pluck from the rocks they override. And as they drag rocks and grit across what lies below, they scratch and gouge and grind them. Ice has plowed and smoothed the Yellowstone landscape. What's more, glaciers have lifted and carried car-sized boulders from far-off locations and deposited them as so-called glacial erratics around the park. One of these, near Inspiration Point, near the Grand Canyon of the Yellowstone River, weighs more than 500 tons and traveled at least 15 miles on ice to get to the place where it rests today. As the ice cap over Yellowstone advanced and retreated, it created dams of both ice and earth that made large, temporary lakes. When these dams failed, they produced catastrophic floods. Geologists conjecture that such floods helped the Yellowstone River to carve the spectacular Grand Canyon of the Yellowstone through soft, colorful, geothermally altered volcanic deposits. It's the geothermally heated groundwater that altered these rocks and transformed them via reactions called chemical weathering into so many pastel hues. If you stand today, as Thomas Moran did, at Artist Point and take in the exquisite vista of Upper Falls and the Yellowstone River about 1,000 feet below, you see the handiwork of both the Hotspots fire and melted glacial ice. The falls themselves exist here because a denser rhyolite lava flow sits atop a less dense one that's more readily eroded by water and carried off. Much of the Yellowstone caldera is covered with rhyolite. The Yellowstone River spills over the edge of the denser lava at Upper Falls and tumbles 109 feet into the canyon, where it continues to erode away and undercut the rocks above. Lower Falls has a drop of 308 feet. In the future, as this erosion continues, Upper Falls will recede upstream away from Artist Point, and the canyon will continue to deepen. In other ways, too, Yellowstone's geological story is far from over. The geyser basins and all their associated geothermal features will continue to evolve, even over our lifetimes. So too, on longer timescales, will the magma chamber and the hotspot below. One day, years from now, hundreds, thousands, tens or hundreds of thousands, the magma chamber beneath Yellowstone will almost certainly erupt catastrophically and collapse once again, reshaping the park we know in extraordinary ways, leaving it unrecognizable. Whether or not this happens, it's quite likely that over the next hundreds of thousands to a few million years, a new magma chamber will arise northwest of Yellowstone and eventually give rise to another caldera eruption of epic proportions. As the land beneath Yellowstone moves further off the hotspot, it will sink and stretch and fracture and fault and those faults will bring basaltic magma to the surface, filling in and paving away the beautiful park that we know and love. And then, perhaps, potatoes will grow above the remains of Old Faithful, the Grand Prismatic Spring, Lamar Valley, and the Grand Canyon of the Yellowstone River. The hotspot deep beneath Yellowstone today has blazed a trail across the northwestern United States. In so doing, it's obliterated mountains and created geothermal wonders in its wake. In its wake, it's flooded the landscape with dark basalt, leaving a high, broad, fertile plain. The magnificent havoc wrought by the hotspot draws visitors from every nation to the world's first national park. In our next lecture, we'll head south from Yellowstone to the youngest mountain range in the Rockies, the Grand Tetons. Together with the sheltering valley beside them, Jackson Hole, these still rising mountains comprise the exquisite Grand Teton National Park.
Photography started for me on a very personal level because I was relatively shy, but I was very curious. And photography gave me an opportunity to come in and fulfill that curious nature. I had an excuse to be there. And that made me so much richer. And there was just something about when I put that camera up to my face and looked through the viewfinder, I just felt organized in a way. This chaotic world I was in became organized in that frame. When I was a National Geographic photographer, I was absolutely convinced I had the greatest job in the world. I believe in the power of photography to instigate positive change. We've got this 100-year anniversary of the Park Service. National Geographic has this incredibly rich history. We need to do a single topic issue of National Geographic magazine with all the bells and whistles and talk about the world's first national park. I said to Nick Nichols, one of the most accomplished photographers of our generation, I said, Nick, come along. I just need your expertise. I need you to show how we work. How you literally, and I'm going to use Nick's words, lay siege. How you come in there and you live, eat, and breathe Yellowstone. Because that's how the great photographs are made. A lunar rainbow, a full moon, a clear night, and there you have it. This rainbow at the bottom of a spectacular waterfall on the Yellowstone River. There's only one way you find that. You're there. Nick comes in and sees this thing he never would have anticipated. And it's magic. The only way you will get the kind of photograph is to want to make the photograph and being willing to say, I don't know what I'm going to find down there. I don't know what it looks like, but I sure wonder